Hello students. So we have already finished chapter 9. So today we will start chapter 10. So this is chapter 10. Okay. And this is the last chapter to cover. So chapter 11 is about abacus simulations. So that we have already tried. So chapter 10 is the last chapter to study here. So this is about beam actually. Yeah. Okay. So we have to first derive equations. So which equation? So let us say there is a beam, the example of beam, let us say this is, so beam, for example, in this case this may be fixed at one end or both end, and there will be a load somewhere. Let us say load is here, or load could be also distributed, so something like this one, so like this, and there will be some force P like this one, and so on. So if that is the case, then how to solve it? Okay. So this is force per unit length, which may be W or sometimes also written as Q, since we have different W has different meanings, so we will use Q in this case. So let us say we have one beam example which is like this one, and we have to find out the deflection. So deflection is let us say this is u is the deflection, which is up and down. This is how it will go. And second thing is u is a vertical displacement. Okay. And du over d theta, so which is a slope. So these two are the degree of freedom everywhere. So that means node will have two variables. So u, one will be u, which is the vertical displacement, and second will be du over dx, sorry, slope du over dx. So x is going like this one, u is up and down, is the displacement of u. Okay. So if the problem is a beam problem which has to be solved, first thing we will need is to actually find out write the equations. Okay. So let's take one small slice from here, from this one here, and we draw it here. So how will it look like? This is like this one. So we have force per unit. So here is Q, which is actually force per unit length. And what kind of force is it? This is the vertical force, transverse force applied on beam. So this is Q. Then we have to apply the other forces. As you know, always what we are going to do, we are going to derive the strong form. Okay. So we will start with the strong forms. Yeah. So a strong form is equal to what? This is what we are going to answer. Right? And in order to know a strong form, you have to know the problem first. You have to know the variables, which all things are there, forces, displacements, those you need to name. Then you have to find out how the forces are being balanced. That's what we are doing right now. So here there will be two kinds of forces. So one will be the shear force. Okay. So this is a convention. This is a down right side and up left side. So this is V is the shear force, and this is V plus dV over dx dx. Okay. So this is what it is here. This is the dx. So this is the variation if the shear force here. So this is right shear force, and there is another type of force here which applies in this case is the bending moment. So M, yeah. So this M is bending moment. Bending moment. All those things you must have done already in solid mechanics or a strength of material class in your second years. So here I am just going to repeat so that you remember all those things so that you can solve the problem. Yeah. So M, if it is M here, so because of the variation M will change. The M will be dm, M plus dm over dx. Okay. So this is how the variation is. Okay. Now balance of forces. So balance of forces, always this is what you do always. So you start with the force balance equation. So first forces in y direction has to be 0. There is no see here, there is no force in x direction, and displacement also we are not concerned about finding displacement in x direction. We are assuming in x direction there is no deflection. Okay. Okay. So this is a pure beam problem, meaning that it is a not axial bar. This is pure beam where vertical deflection and slope are the only degrees of freedom. Okay. So Fy, total force in y direction, has to be 0. So then we have Q, we have V, we have V plus dV over dx. Okay. So only these forces are which are in vertical direction. So this means summation of all the forces in y direction has to be 0. That really means V. So V is up, then Q is down. So B minus Q times dx. Q times dx because Q is the force per unit length. So length is dx. So that becomes V minus Q dx, which is downward, and then this also downward. So plus minus V minus dV over dx. Okay, has to be equal to 0. And what does it tell us? It tells us V, this V minus V cancels out. So and then we simply get Q plus, okay, so V minus V equal to 0, then we multiply by minus 1, so we get Q here, Q plus dV over dx equal to 0. That's what we will get from here. So finally we get dV over dx equal to minus Q. So this is what we get relationship between the shear force and the loading Q. This is the relationship. Now similarly we can work for finding out the moment. Total moment has to be equal to 0. So total moment equal to 0. Okay. If we do that, what do we get? So let us see. So total moment equal to 0. So look here. So we have m plus dm over dx minus m. So let's start writing here. So we have m plus dm over dx. So this is m minus this m. So minus m. Okay, and then there will be moment because of this one, this is making it clockwise, so will be v times dx, so minus v times dx. Okay, so next will be because of this q, so force is this will make anti-clockwise, so m is clockwise, due to v will be clockwise, due to q will be anti-clockwise, and hence it will add up. How much? Add up like plus q times dx is the total force, q times dx is the total force, and we have to make it moment, so moment is the lever will be dx over 2, so force is q times dx, lever is dx over 2, so that's why we write q dx and dx over 2, everything becomes equal to 0. Okay, so what do we get? M minus m cancels out, so we have dm over dx, then we have minus v dx, and then plus q, and here we have dx square over 2 equal to 0. Now this is second order term, dx square, so we will make this equal to 0 because this second term, so we will be neglecting it, and here what we get simply is, in that case, dm over dx equal to v. So this is the second relationship we get for the force balance. The first one was dv over dx equal to minus q, and second is dm over dx equal to v. So just write the first one, as I said earlier, this is dv over dx equal to minus q, this is the first one. Okay, so we combine them together, and what do we get? So this dv over dx equal to minus q, but v itself is dm over dx. So we put this one to the here, so put here to here, and what we get? We get d over dx, so d square m, so d square m over dx square equal to minus q, simply. Yeah, so we put in this one, we put the value of v, so the, v is dm over dx, so this becomes d square m dx square equal to minus q, or simply we get d square m over dx square plus q equal to 0. So this is the final force balance equation, right? So this is the force balance equation. Okay. Now notice that we have this equation which is a force balance equation, but finally we have to solve a equation. Finally we have to solve for u, where u is the vertical displacement. So we want equation to be in terms of u, that is possible only when we know how m relates to u. Q is given, but m is not given here. So q is known, but m is not known. So that means m, we have to ask the question, how is m related to u? Okay, unless we know that, we will not be able to solve for u, so that's why we have to find out. Okay, so this can be done in 2 steps. So what we have to know? First we have to know how is a strain related to u, or is also called kinematics, right? Okay, and then second thing is how is a stress related to a strain. Okay, so or since a stress, or how is a stress, actually 3 things. So how is a stress related to a strain? that's the second thing, just a material property. Okay, so material properties. Okay, and then number 3 is how is a stress related to force. Okay, so force in this case is bending moment M. Okay, so if we combine all those 3, we will get M in terms of U, and that we can put it there. Okay, so that's what we have to do now. So let's look at them one by one. Okay, so number 1 is how is a strain related to U. Okay, so this is the question. Okay, so for that we have to go back to what you did in the solid mechanics class, that is the strength of materials class. So let's draw the diagram that you drew there. So if this is a beam under pure bending, okay, so if you extend here, okay, it will move somewhere, and let us say this is theta angle. If this is the neutral axis, okay, then distance from the center, so let's center is somewhere here, so this is the center. Okay, so this is the center. So distance from the center, that is from here to here, will be, let's call it rho. This is the radius of curvature. For the neutral axis. Okay. Now let's consider a point here. So this one. Okay. So distance here, let us say this is distance is U. From here to here it's y. This is the distance from here to here is y. Okay, so consider that point. So then radius of curvature for this point will be, if we consider at this point, the radius of curvature of this one will be rho minus y. Okay. Okay. Now a strain, let's call a point P. Okay, so a strain at point P is equal to, becomes change in curvature, the curvature, the radius of curvature here. So that will be simply theta times radius of curvature at point P. So this will be theta times rho minus y. This is the total circumferential area, or means arc length from here to here actually, minus at the neutral axis the original length was rho theta times rho. Because at the neutral axis there is no change in length, hence the original length is rho multiplied by theta. Theta is the angle here. This is the final length, this is the original length. If this were not bent like this one, the original length at P, means from here to here, would have been theta rho only. However, since it has been bent, because of that radius of curvature at point P has changed from rho to rho minus y. Hence, change in length at y from the neutral axis will be theta times rho minus y minus theta rho divided by theta rho, which is the original length. Okay, so let's call it this one, or this becomes a strain at coordinate y, okay, at height y from the neutral axis is given by minus y over rho. Okay. So, what it tells you? This tells you how the strain related to the how is a strain related to y. That's what it gives you. Still, this has not given us how a strain relates to u as yet, but this tells us how a strain relates to y. Okay, so that means if there is a beam like this one, and if it is bent, then our x goes like this one and y is like this one. So depending on the y coordinate of a point, you can calculate what the strain will be if you know the rho. Okay. Rho may have displacement. Okay. So if we somehow get rho as a function of displacement, then a strain here will be also a function of displacement. So that's what we have to find out now. So now the question is can we find rho in terms of u? So that's the question. Okay. So let us say this beam, when it bends, this becomes something like this. So this is the how the beam becomes. So let's consider 2 points. So here and here. Okay. So 2 points is like this one. Okay. So let's say this is P, this is Q. So this is P, this is Q, and here there will be some angle here. Okay. So this is theta P, and there will be slope here also. So this is theta Q. Okay. Okay. And if we say d theta equal to theta Q minus theta P. So if you take perpendicular to this one, from here also perpendicular to this one, where they meet, this angle has to be d theta. Okay. So that means normal has rotated by d theta. That means the angle with respect to horizontal will also increase by d theta. Hence d theta equal to theta Q minus theta P, which is like this. Okay. Now if rho is the radius of curvature like this one, so we write rho here, and the idea is to find out how rho is related to u. Now these are the displacements. So let us say at here the u at P is up like this, and this one is u at point Q is Q. So this and these are vertical displacements. Okay, so vertical displacements. Okay, just like this one. Okay, so how are they related? Okay, so for what we know right now is we have from here to here, let us call it ds. Okay, so this is ds. Okay, so ds is equal to, it will have, so if ds is like this, ds is very small, so ds is here, ds is like this, so this is dx, this is dy, and this is what the theta will be. Okay, so ds equal to root under dx square plus dy square, hence dx root under 1 plus dy over dx square. Okay. Now dy over dx is this over this one is also tan theta, so we can also write equal to, so this becomes dx root 1 plus tan square theta. So this becomes 1 plus tan square theta is sec square theta, hence you get sec theta dx. Okay, so this is what the relation we got from like this one. By the way, here we have remember, whatever we are getting upward is nothing but u. This is not y but u, so let's correct it. So dx square and du square, so we are talking about the deflection. So here this is u, so any point P has x and u coordinate system. Okay, so we write du square, so du over dx, and like this one, so here also we write du, so dx du. Okay, so dx and like this one. Okay, so what we got so far, we got ds equal to sec theta dx, or simply we got ds over dx equal to ds over dx equal to sec theta. Okay, now as given here, so we have ds du over dx equal to tan theta, so we will write it here also. So here we have ds over d theta, but remember, in order to find out rho will be equal to ds over d theta. This is rho is, right? So this is the total curve length divided by angle will give you rho, because curve length equal to rho times d theta. So we have to get ds over d theta. Okay, then only we can get rho. But remember, we have ds over dx equal to sec theta, but we have to know ds over d theta. So what we need is, if you multiply it by dx over d theta, then we can multiply dx over d theta to this one, and we will get the value of rho. Okay, so basically rho equal to ds over d theta equal to ds over dx and dx over d theta. Okay, so the question is now dx over d theta equal to 1. So if we get this one, then we can get the value of rho automatically. Okay, in order to find out, we have to use some trick here, and what is that? We know that du over dx equal to tan theta, that we know that. We differentiate again. Okay, so if you differentiate again, we will get d theta over dx term here. So d square u dx square equal to tan theta. So this becomes sec square theta, and then d theta over dx. Okay, so that really means we can now get the value of d theta over dx equal to nothing but d square u over dx square, d square over dx square over sec square theta. Okay, d theta dx equal to du over dx, d square u over dx square over sec square theta. Okay, so we have d theta over dx term. So we put it here. So we get rho equal to ds over dx multiplied by dx over d theta. But what we have is d theta over dx, right? So we have ds over dx, okay, ds over dx divided by d theta over dx, right? So what we get? ds over d theta. So ds over dx is sec theta. So we write sec theta here, sec theta divided by d theta over dx, d theta dx is this one. So what we have is d square u dx square divided by sec theta. So we write sec square theta here. So what we get? Sec cube theta. Okay, so d square u dx square. Okay, but again theta we don't know. Basically theta is the intermediate term, so we have to write theta in terms of u, and what we know is tan theta is equal to du over dx, right? So that means what we know is we have to write sec theta in terms of u now, so that rho is absolutely in terms of u only. So tan theta is equal to du over dx. So that really means tan square theta is equal to du over dx square, which is equal to 1 plus that's my sec square theta minus 1. Why? Because sec square theta equal to 1 plus tan square theta, hence like this one. Or simply what we get? We get sec square theta equal to 1 plus du over dx square, like this. Yeah, and hence what we get? We also get sec cube theta equal to becomes 1 plus du over dx square, and power will be 3 over 2, like this. Okay, because sec square theta equal to like this one, sec theta becomes root of this, so sec cube theta becomes 3 times half, so 3 over 2. So this is what the sec cube theta will be, like that. So we have sec cube theta equal to this expression, and then what we have to find out? Rho. So rho has this expression, so sec cube theta is this one, so 1 plus du over dx square to the power 3 over 2. So that's what we have to write here, divided by d square u over dx square. So that's what we'll write, equal to rho. Okay, so rho, that really means the rho equal to sec cube theta. So sec cube theta is equal to 1 plus du over dx square to the power 3 over 2 over d square u dx square. So this is what the rho is. Okay. Now remember the strain, what we got was a strain equal to minus y over rho. Okay, so that means a strain, if we write a strain now, that will be equal to by the way, here we are assuming this theta is to be very, very small. Okay, so this is a linear beam deflection problem, linear problem, meaning that du over dx is very, very small, and that really means the rho will have only 1 over, so this is equal to 1 over del square u dx square. Okay, assuming, if we write here, assuming del u over del x very small. Okay, very small. Okay, so what we get, if rho is equal to like this one, so hence from here we get 1 over rho is equal to d square u dx square, and once we know that, so we get a strain equal to minus y times d square u dx square. So this is what the strain is. Okay, so we get a strain, we get this way we get a strain in terms of u now. Okay, so the first task is done already. Okay, now the second task is a stress in terms of a strain. So it's easy. This is because we know that sigma is equal to like this. So we get sigma is equal to minus e y d square u dx square. So this is very easy. So a strain equal to minus u y d square u dx square, and a stress E times a strain. So sigma equal to minus E y d square u over dx square. Okay, done. Now what is next? So we have to find out 3. Okay, we have to find out relation. Say m in terms of, so how is a stress related to forces, right? Forces. So a stress in sigma related to forces, in this case m. So finally all the original equation in terms of m only. So we have to find out m and sigma, whether there is a relation, so that we can put m here, and we can replace sigma with m, and we will get this the equation which will have u and the m there, and once we have m in terms of u, we can put this value in the original equation, right? So okay, so how is the stress related to two forces M. That's what we will do now. Now remember this d square u over dx square is nothing but 1 over rho only. So basically what it means is E y over rho. That's what that is, right? So we will start from here. So sigma is nothing but sigma equal to minus E y over rho. Okay, now if for a pure bending, if with a pure bending, we will have a pure circle here. Okay, so this will have rho, where rho is the here rho is the radius of curvature. Okay, so radius of curvature for the neutral axis, which is constant when we have a bending moment, which is only bending moment is being applied. So M is like this one. So this M has resulted into bending of this, and this has a radius of curvature rho, and this is very small. So from here to here, as I said, this is d theta from here to here. So if that is the case, so relationship will be sigma equal to minus E y over rho. Okay. Now look at one section like this one. Okay. So if you draw a section will be something like this one. Yeah. Okay. Now what it says, if y equal to 0, sigma equal to 0, so it's neutral axis, sigma equal to 0. If y is positive, you go up, and then since y is positive, E is positive number and rho is also positive number. So what you get is a negative number. So what you have is a stress which is negative. Yeah. So something like this one. So you have a stress which is negative here and a stress which is positive here, and value is given by sigma equal to minus E y over rho, and this one what you say is linear from here to here because it varying with y. At the neutral axis, stress is equal to 0. So this is a stress profile. If that is the case, then what we have to find out? We have to relate. What? We have to relate M with a stress. How is a stress related to the how is this stress related to the force? Okay, so if the given sigma, can you calculate the force? That's the question. Okay, so how can we do? Okay, so in order to do that, what we have to do is we apply the equation of equilibrium here. Okay, so equilibrium, we have to look at the equilibrium. Okay, so first thing will be the forces, all the forces in x direction has to equal to 0, and what we have, this is sigma, which is a function of y. Okay, so that really means for the whole section, this is the section. Okay, this is section. Okay, so for the whole section, we have to sigma times dA. Sigma times dA has to be equal to 0. Okay, this is equilibrium because total force at this section has to be 0 because there is no this is for equilibrium. At any point, if the point is in equilibrium, that means total force has to be equal to 0. Hence total force, this is total force, so Fx has equal to 0. That only tells you sigma is minus E y over rho and dA. Now this is very small portion of the beam. Rho is can be considered as constant. So rho is constant, E is constant for the whole element of length rho d theta. So what we get simply is total force Fx is equal to minus Ey over rho dA. E and rho is constant, so minus E over rho, and you get U dA, and you know that total has to be equal to 0. So that really means U dA equal to 0. Okay, so this is one thing we got. That really means the coordinates, the origin of the coordinate, that's y equal to 0, is where the centroid of the area is. So this really means the neutral axis, simply neutral means neutral axis passes through the centroid, centroid of the section, centroid of the beam sections. That's what that really means. Okay. So that we get one information. Second information means second equation of equilibrium we can get if we apply the bending. So we want to find out total bending will be equal to total bending moment has also equal to m. So at this section bending moment is m, hence we have to integrate sigma over the whole section, and that should give the result equal to m. Okay, so if the profile of the bending moment is like this one, so we have like this, like this, so this, and y from here the y goes like this one. Yeah, so that really means sigma times y is the lever actually. The sigma times y will be the lever multiplied by sigma multiplied by dA. This is the bending moment m it should give. Okay, so that, but sigma is equal to, we know that sigma equal to minus Ey over rho. So minus Ey over rho. Okay, so minus Ey over rho is the sigma multiplied by U dA. Okay, so what do we get? Or m equal to minus E over rho, and here we get y square dA. Okay, so that really means what? That really means m equal to, this is also called E over rho times I. This is nothing but the second moment of area or moment of inertia simply. So this is what the I is. Yeah, so we get like this one. So what you get? You get m equal to minus E over rho times I. However, we have to do a small correction, and that is because the convention of m is when it is like a sagging condition, something like this, so which is anti-clockwise at the right end and clockwise at the left end, which is assumed to be positive m, right? And remember that the stress here is negative because compressive, because when you are bending like this one, the above fiber will be in compression, hence the stress will be negative. So what we see as if you multiply negative stress multiplied by positive lever will give you a negative number. Similarly here, positive stress multiplied by negative lever y gives you negative. So in order to make it positive, actually m has to be equal to minus, like this one, hence minus here, so we get like this, okay, plus plus, and here also m equal to e I over rho. Yeah, so m finally equal to e I over rho. Okay, so this is the equation. Okay, anyway, all these things are nothing new. All these things you have already studied in the solid mechanics class. Okay, so if you are still confused, I advise you to go through those solid mechanics books that you refer to during your second year solid mechanics course. Okay. Okay, so next is we can replace rho with 1 over rho with the equation we know already. So m is equal to ei times 1 over rho, and 1 over rho is, we know that, is equal to d square u over dx square, right. So we have finally m in terms of d in terms of u, right. So combining all those things we get this one. So okay, not to forget our original equation. Our original equation after force balancing was d square m over dx square plus q equal to 0, where m now we have got m in terms of u, so we will put that value now. So the original equation was equation of equilibrium del square m dx square plus q equal to 0. Now m value you put here, so finally what we get? We get d square dx square, and m value is this one, ei d square u dx square, right. So this value plus q equal to 0. So this is what the final strong form. Of course, there will be the boundary condition along with this one. A boundary condition will be either the displacement will be given, for example, one end may be fixed, different kind of the end may be fixed differently, so that you know, and there may be forces given. So that is the natural boundary conditions. Okay.